Welcome to the Zoom room, and we'll just get started right away. We're on a mechanics test, mechanics, the summer of 2021, May, June 2021, and paper 42. So let's get right into it here. And for question number one, a particle of mass 0.6 kilograms is projected with a speed of 4 meters per second down a line of greatest slope of a smooth plane inclined at a 10 degrees to the horizontal. Use an energy method to find the speed of the particle after it has moved 15 meters down the plane. So a lot of or first strategy in being successful in the mechanics paper is being able to draw a diagram that accurately represents the situation. So here we have our inclined plane with the horizontal at 10 degrees. It's starting at the top with a velocity projected at a speed of 4 meters per second. It's going to move 15 meters down the plane, and our goal is to solve for the velocity at that point. And it asks us to use an energy method. Well, there's two energy formulas. One is potential energy, which deals with height, and the other one is kinetic energy, which deals with your initial and final velocity. Well, we have the initial velocity, we don't have the final velocity. So it's a little difficult to use kinetic energy at this point. So we're going to focus on trying to establish potential energy. But to do that, we need to find the height. So notice I make this right triangle with the positions of the object in its initial position and final position. And using SOHCAHTOA, we get sine of 10 degrees is opposite over hypotenuse. So then to solve for h, the height, we just get 15 sine 10 degrees, and that's 2.6047. And because this is a smooth slope, meaning there's no resistance or friction, we can put this into our potential energy formula. 0.6 is our mass, 10 is the gravity, and 2.6047 is the height. So we get 15.628 joules. And again, because there's no resistance, that means our potential energy is equal to the buildup of kinetic energy. That is the loss of potential energy, because we went down, will be gained in kinetic energy. So we can take that 15.628, plug it into our kinetic energy formula, which is 1/2 mass times initial velocity minus final velocity. And when we solve for our, that is our final velocity minus initial velocity, when we solve for our final velocity, we get v squared equals 68 and v equals 8.25. So starts off at 4 meters per second and ends up at 8.25 meters per second going down the slope. Question number two, we have 3 forces that are given here, 34 newtons, 30 newtons, and 26 newtons, and at the directions that are shown. Given that sine alpha equals 5/13 and sine theta equals 8/17, find the magnitude and direction of the resultant of the 3 forces. So this is resolving forces, and then it's not in equilibrium, it is finding the resultant force. So we want to resolve all 3 of these forces with the x-axis. Notice that our angles are not against the x-axis. So we need to deal with that first. We have alpha and theta, they are both up against the y-axis. So we want to resolve this with the x-axis. So if you notice, this one here is a 5, 12, 13 right triangle. And So we just put it up against the x-axis here. And so the 90 minus alpha, that is our 90 degrees in this quadrant, minus the alpha with this angle here, will be 12/13 because we're doing sine. It gives us sine here. So sine is the opposite over hypotenuse. So it gave us the 5 and the 13, and then we come up with the 12 with your Pythagorean theorem. So 12/13 will be the sine of the angle that's next to the x-axis. Same thing with the 8 and 17. It gives 8 and 17. You use the Pythagorean theorem, you can find the 15 for the height, but put it over here against the x-axis. So sine of this 90 minus theta is going to be 15/17. So we have to adjust those first to be next to the x-axis. Now we can resolve the forces. So I start up here in the upper left with the 34 newtons in the upper left and multiply it by the sine of the angle, which is 15/17. That gives 30 newtons going straight up. This is resolving it in the vertical direction. If we resolve it in the horizontal direction, that means we take cosine of the angle, which is 8/17. So 34 times 8/17 is 16 newtons going to the left. As we move clockwise around, we get over to this 30. It's just going straight along the x-axis. So there's really nothing to resolve there. It's just going to the right at 30 newtons. Then we come down here to the 26 Newton one, and we resolve it going down. So that's using the sine, which is our 12/13 times 26 gives us 24 newtons, resolving it to the left using the cosine value, 5/13 times 26 is 10 newtons. Then we resolve all the forces by taking the up forces minus the down forces. So the up forces was 30. The combination of the down forces was 24. 30 minus 24 gives us a resultant force of 6 newtons in the upwards direction. Then we take the right minus the left, which is our bigger minus the smaller. 30 minus the 2 forces going left. 30 minus 26 is 4 newtons going to the right. So we want both magnitude and direction. So with magnitude, we just basically find the hypotenuse. We have a resultant of 4 to the right and 6 up. So using the distance formula here, or the Pythagorean theorem, a squared plus b squared equals c squared. So our 4 squared plus 6 squared at 16 plus 36 is 52. The square root of that is 2√13. Which you could put that or put the decimal form. 7.21 newtons is the magnitude. Then to find the direction, make sure you're careful when you find the direction that you give kind of some details with that. So to find the direction, you take tangent of the angle, which is opposite over adjacent, reduces to 3/2. Take the inverse tangent of that, you get 56.3 degrees, but you need to give some sort of indicator of where you're at. So it's 56.3, I believe it was, degrees above the positive x-axis. If you were in the second quadrant, it would be above the negative x-axis. If you're in the third quadrant, it would be below the negative x-axis. And if you're in the fourth quadrant, below the positive x-axis. So make sure you're clear on your direction. 56.3 degrees above the positive x-axis. Number 3, a ring of mass 0.3 kilograms is threaded on a horizontal rough rod. The coefficient of friction between the ring and the rod is 0.8. A force of magnitude 8 acts on the ring at an angle of 10 degrees above the horizontal of the vertical plane containing the rod. Find the time taken for the ring to move from rest 0.6 meters along the rod. So again, first start with the diagram. Here's my rod. Here's my ring going around the rod. Because it is a rough rod, there's a friction force pointing to the left, because my force that's acting on the ring, the 8 newtons, is to the right at 10 degrees to the rod. And because this is going to move, we're going to have 0.3, we're going to have a mass times acceleration. In other words, there's going to be a net force because there's movement here. So 0.3, and the movement's not constant. So 0.3 times A, our coefficient of friction is 0.8. I put that over here. We also need to resolve these forces with the rod. So 8 times sine of 10 degrees is 1.389. That's going up. That is important because it goes against the weight of the ring going down, which affects your normal contact force. I didn't draw in the normal contact force. That is the force pushing up by the rod onto the ring itself. So I didn't draw that in, but there is a normal contact force acting against the ring here. Then going this way, which is going to be the part of the force pulling the ring along the rod, 8 times cosine of 10 degrees gives us 7.878 newtons to the right. So let's find our force due to friction. So we take our mu, that is our coefficient of friction, 0.8, multiply it by the normal contact force, which is your forces resolved vertically on the ring. So that's 3 newtons down minus the 1.389 newtons up. A lot of students forget to subtract this upward pull from this diagonal force here. So don't forget to do that. So your overall force of friction is 1.289. Now we go to our net force, which is like our total of all forces. Mass times acceleration, 0.3 times A equals, and then we have our force pulling to the right, 7.878 minus the force of friction, 1.289. And so our acceleration is 21.96 meters per second squared. I didn't put the units there, meters per second squared. Now we are given distance, 0.6 meters. So we're going to use a Suvat distance formula because we have acceleration and we're looking for amount of time that's taken to move. So our distance is 0.6. Our initial velocity is 0 because it says that it's from rest. Time is what we're solving for, plus 1/2 A. We just calculated that, 21.96 t squared. So we end up with t squared equals 0.0546. And time then for that moving of 0.6 meters is 0.234 seconds to 3 significant figures. Question number 4, a particle of mass 12 kilograms is stationary on a rough inclined plane at an angle of 25 degrees to the horizontal. A pulling force of P newtons acts at an angle 8 degrees above the slope of the plane. This force is used to keep the particle in equilibrium. Equilibrium means that there's no acceleration, which also means there's no net force. The coefficient of friction between the particle and the plane is 0.5. Find the greatest possible value of P. So again, let's start with our diagram. Inclined plane at 25 degrees. Here we have our object, 12 kilogram object on the inclined plane. So we need to resolve its mass with respect to the plane. So 12 times 10 is 120 Newton straight down, times sine of the angle 25 degrees gives us 50 0.714 newtons in the downward direction. We also need the normal contact force. Our normal contact force, or at least first, let's resolve the force going up. We have to take care of this little piece over here as well. Our force going up is 120 cosine of 25, which is 108.757. So it's not the normal contact force yet. We also resolve our force P. So P sine 8 degrees is going up, P cosine 8 degrees is going up the slope to the right. And this is P sine 8 degrees is going against your downward force. So let's put all this together. Remember, it's in equilibrium. So all of your forces that are going up the slope are in equilibrium or equal to the forces going down the slope. So there's only one force going up the slope. That's P cosine 8 degrees. Then that is going to be equal to all the forces going down the slope. Well, the 50.714, that is the resolved force from gravity of the object that is resolved down the plane. And then this part right here is our friction. The friction is the mu coefficient, 0.3, times the resolved vertical forces. So there's 108.757 down minus P sine 8 pulling up. So we've got everything now down to our letter P. We just got to get the P by itself. Over here, we get 0.99 P equals all of this. Distribute your 0.3 through. 0.3 times sine 8 is 0.04175. Add this P here over to the 0.99, get 1.031 P equals, add those two together, get 83.341. Divide and you get your force of P is 80.8 newtons. Make sure you're taking your decimal place far enough for your final answer to be correct to 3 significant figures. You should do your work where appropriate to 4 significant figures or more. Going on to number 5, a car of mass 1,250 kilograms is pulling a caravan of mass 800 kilograms along a straight road. The resistances to the motion of the car and caravan are 440 newtons and 280 newtons respectively. They're connected by a light rigid tow bar. So part A, the car and caravan move along the horizontal road at a constant speed of 30 meters per second. Well, constant speed means there's no acceleration, which also means there's no net force. So if there's no net force, we're going to want to deal with our caravan or our car and caravan as a whole. And so here is the car going to the right with the driving force over here. Here's the tow bar with tension pointing both ways. You only need that if you separate your objects. If you treat it as a whole, you don't need to pay attention to the tension. Here's the caravan in the back, and there are the respective resistances to the car and to the caravan. So since this is in equilibrium because it's at a constant speed, there's no net force, then that means the driving force is equal to the sum of the resistance. So the driving force equals 440 resistance on the car plus 280 resistance on the caravan equals a driving force of 720 newtons. Now, the question says, calculate in kilowatt hours the power developed by the engine of the car. So power is force times velocity. The force we just figured out was 720. The velocity was given at 30, and you get 21,600 watts. Convert it to kilowatts, 21.6 kilowatts for the power of the engine. Now, given that this power, that's the 21.6 kilowatts, is suddenly decreased by 8 kilowatts, find the instantaneous deceleration of the car and caravan and the tension in the tow bar. So since we need to find tension, we're going to be separating the car and the caravan into separate parts. Let's start with our power. We started with 21.6. We have a sudden decrease by 8 kilowatts, meaning we're now dealing with 13.6 kilowatts, which is 13,600 watts. Our 13,600 watts is the power divided by the 30 meters per second. That is our speed. That is still our speed. Gives us a new driving force. In other words, the driving force dropped to 453.3 newtons. Now, because of the power decrease, there is a deceleration that happens. So now that we have deceleration, we now have a net force. So our net force, using the mass of the car and the caravan separately, allows us to come up with simultaneous equations because we're solving for both acceleration and tension at the same time. So for the car, 1,250 kilograms times the acceleration equals the driving force minus the force of resistance minus the tension in the tow bar. And for the caravan, 800 kilograms times acceleration equals the tow bar minus the resistance. So notice we're going to the right. So for the car, it's the driving force minus the resistance and the tension, but for the caravan going to the right, it's the tension minus the resistance. So this is just simultaneous equations. I got the T in the second equation by itself, plugged it into the first one, distributed this negative here through the 800A plus 280. This is the 453.3 minus 440 right here. Get the A's on the same side together. Get your other values. Notice it's negative. That's because we're dealing with deceleration, not acceleration. So it means we're slowing down, not speeding up. So our acceleration is a negative 0.13 meters per second squared, or you could call it decelerating at 0.13 meters per second squared. Plug that into our tension little equation that we got here, and your tension is 176 newtons. Going on to part B, now our car and caravan are going up an inclined plane that has an angle of inverse sine of 0.06. So that means if you just multiply, that's the angle. So if you sine both sides, that means sine of the angle is 0.06. The car and the caravan are going at a constant speed. So again, there's no acceleration, no net force, and the engine is working at 28 kilowatts. Find the constant speed at which this car and caravan are going. Again, draw yourself a good diagram. Here's the car and the caravan with their resistance is the same as before. The tension in the tow bars for each car and caravan, the driving force going up. Now we're dealing with a slope. So we need to resolve our mass down the slope. So 8,000 or 12,500, which was our car up here, times 10 gives, or 1,250 times 10 gives 12,500, times sine of the angle, which is 0.06, gives us 750 newtons for the car that's pulling downhill. Resolve the force for the caravan, 800 times 10 is 8,000, times the 0.06 gives us 480 newtons. Since this is in equilibrium, because it's constant speed, that means the driving force is equal to the sum of the resistance forces plus the sum of the resolved forces due to gravity. You add all those up and the driving force is 1,950 newtons. And to find velocity, we can take our power formula. Power equals force times velocity. Our power was 28 kilowatts or 28,000 watts. And our driving force is 1,950. Divide that over into the power to get the velocity, 14.4 meters per second. Then in the last section here, find the increase in the potential energy of the caravan. It's not the car, just the caravan part in 1 minute. Well, we got our speed, everything, both the car and caravans going the same speed. So 14.4 meters per second for 1 minute, 60 seconds per minute. Seconds cancel out, you now have meters per minute. So in 1 minute, you will travel 861.54 meters going up this slope. So we can use that to find the height. So sine of the angle equals height divided by, or the opposite divided by hypotenuse, Sokolah. So sine of the angle, remember we were given that up here, 0.06. So 0.06 times the 861.54 gives us a height of 51.69. That's a vertical height. So plug that into our potential energy equation where there's going to be a gain in energy. The mass of the caravan, remember you're dealing with the caravan only, 800 kilograms times 10, that's your gravity, times the vertical height gives a potential energy gain of 413,520 joules. If you put that to three significant figures, it's 414,000 joules for potential energy, which is what it asks for, the increase in potential energy. Okay, moving on to number 6. Wow, here we have an 8-point problem. We're going to get into a multi-stage problem here. Particle A is projected vertically upwards from level ground with initial speed of 30 meters per second. At the same instant, the particle B is released from rest at 15 meters vertically above A. The mass of one of the particles is twice the mass of the other particle. During the subsequent motion, A and B collide and coalesce to form particle C. Find the difference between two possible times at which C hits the ground. Okay, so this is multiple stage on several levels. First, you're dealing with this projection and time that it takes for the objects to hit the ground. So this is, since your gravity acceleration is 10, is constant, means you're dealing with Sokolah, your distance velocity acceleration unit. And also because our objects collide and coalesce, we're also dealing with momentum unit. So let's draw our diagram. We have A being projected from the ground at 30 meters per second. Then at the same time, from 15 meters above the ground, B is being released from rest. That means from 0 meters per second. Somewhere in between, I just put it in the middle. It's definitely not to scale. We find out later this over here, that B only drops 1.25 meters and A goes all the way up to 13.75 meters. But we don't know that right now, that we calculate later. So they meet somewhere in the middle and they coalesce. So now I call it object C. And these are the masses. Remember it said the mass of one is twice the mass of the other. So for my diagram, I have object B just be mass M. And so the other one is twice the mass. So A is 2M. And that means when they coalesce, they become one mass. So m plus 2m is now 3 m's. This m is not meters. This m up here for 15m is meters, how high it is. This m is the mass of C, and then it falls back to the ground. Actually, what I don't have in the diagram is when these two collide, especially since this one is just released, it doesn't have a chance to build up much momentum, velocity times mass. This one is traveling at a velocity, higher velocity. Because I started off with twice the mass, it has heavier mass. When these two hit and coalesce, the object will actually go up until gravity causes the velocity to reach 0, and then it's going to fall down again. So there's a little up and down movement here that's not drawn into my diagram. Okay, so you need to account for that, how far up it goes till it reaches velocity of 0, and then how far down it goes to hits the ground. So for right now, we can worry about that later. Right now, we want to find out how much time it takes before the objects hit each other. Okay, so the total distance that's covered is 15 meters. Again, we're going to use our Suvat formulas for distance, the distance that A covers plus the distance that B covers. So the distance for A is going to be its initial velocity times time, 30t, plus 1/2. And from the perspective of A, your gravity is pulling you back toward A. So that's going to be a -10, 1/2 times -t squared. Because our reference is A and gravity is pulling you back toward A. Then for object B, our point of orientation is now changed. It's up here. So initial velocity of 0 because it's released at rest, plus 1/2. Now our A is going to be positive because from our point of reference of B, gravity is pulling us away from the origin, not back toward the origin like it was with A. So with A, it's -10, and with B, it's +10. Gravity is pulling you away from your origin. Simplify this out, you'll find out that your t squares actually cancel out. You're left with 30t equals 15, t equals 0.5 seconds. So then I plug the 0.5 seconds into a velocity Suvat formula to find out what their velocities were when they collided. So the velocity, the final velocity of A equals initial velocity plus our -10 times 0.5, which was the time taken, means it's now going 25 meters per second at the collision. I could have drawn in another arrow here with 25 at the collision point. And for object B, its final velocity equals initial velocity at rest plus a +10. Again, it's pulling you away from your point of reference, times 0.5 the time, and you get a velocity of 5. So it's going 5 meters per second upon collision. So that's where I did this work here with this Suvat formula, just kind of checking out our distance and making sure it adds up to 15. So for the part B, 1/2 u plus v times t equals 1.25 meters. That particle B fell, and particle A went 13.75 meters up. So remember, this 3m is not meters, it's mass combined here. So this dot actually should be like way up here if you're putting it to scale. B only falls 1.25 meters. A goes all the way up 13.75 meters. Just keep that in mind. Now we're going to get into our 2 different scenarios. Notice it says find the 2 possible times at which C hits the ground. Well, scenario number 1 is the way that I drew it. B is mass M, and A is twice the mass of B, giving us 2M. Where am I at? Right here, scenario number 1. Scenario number 2 is that A is the M and B is the 2M, the B being the 2 times mass A. Okay, so that's our 2 different scenarios. It says one is twice the other, but it doesn't say which one is which. So this is what creates our 2 scenarios. Now we can do a momentum before and after equals the coalescence. So part A, 2 times M is its mass, times its velocity at impact. And since it's going up and particle B is going down, we're going to take the larger minus the smaller. They're going in opposite directions. So when they collide, it's either got to go this way or this way. You take the larger minus the smaller. So the going up is larger. That's 45 M minus particle B was going 5 meters per second when it hit, and it has a mass of M. So 50 M minus 5M is 45 M, and that's going to give us a combined mass of 3M times the velocity at which it's going at impact or just after it impacts. And notice the M's cancel out. You can divide those out, divide by 3. So that means your velocity is 15 meters per second in the upward direction because you did up minus down. In the second scenario where A is M, so M times 25, minus the 5 times 2, we still see that the up momentum is larger than the down momentum. So we get 25M minus 10M is 15M. We still have 3mv for the right because the coalesced mass is 3m times the velocity. The m's cancel, divide by 3. You now have 5 meters per second in the upward direction for scenario number 2. So what we need to now figure is how much time do each of these coalesced objects need to reach a final velocity of 0. That is, how much time does it take for it to go up before it stops going up and then it falls down to the ground. So our final velocity will be 0. Our initial velocity was 15. Again, now we're with respect to the ground. So we have a -10 acceleration and we're solving for the time. So for this one, we get 1.5 seconds. We do the same thing over here, but we're starting with an initial velocity of 5. And so we only get 0.5 seconds for this one. So they stop going up at 2 different time here, these 2 scenarios. Now we add up the distances that they traveled to find out how high the coalesced object reached. Okay, so here's our 1/2 u plus v times t. So how far did it go after it coalesced in the upward direction? So here's 1/2, 15 was our initial velocity. It's going to stop at 0 degree, not 0 degrees, but 0 meters per second. And it took 1.5 seconds to reach that 0 meters per second. So that means this scenario 1 coalesced object went back up after they collided, went back up 11.25 meters. 11.25 meters, so quite a way, plus the original height at which they collided. So remember, they collided at 13.75 meters from the ground. Then because of the momentum, it continued up another 11.25 meters. So it's now at 25 meters high. It's higher than what particle B started with when it was first released. And that's because A was projected with a higher velocity, had higher mass in this particular scenario, and so the impact drove it back up. In this scenario here on the right, the velocity is less, and when you plug it in, and also the time traveling is less. So it only goes up 1.25 meters plus the original collision point, means it reaches 15 meters, which was the original distance that B was dropped from. So B is dropped, collides with A, that coalesced particle, because of momentum, goes back up to that same 15-meter mark at which B was originally released from, and now its velocity is 0. Now from that, so we have 25 meters height where a coalesced object is now at velocity 0, 15 meters for scenario 2. Now we can use our distance formula with our acceleration and find the time that it takes for these two scenarios to meet the ground. So they both have now an initial velocity of 0 because it's reached the high point. It's now going to drop to the ground. The distance is 25 meters. Acceleration is 10. Why is it positive 10? Because our point of reference is from the height. It's pulling you away from that starting point of where it starts to fall. So it's in the positive 10 direction. Your point of reference is not from the ground, it's from the falling point to the ground. So that's why the 10 is positive in both of these. So you solve for T, you get 2.236 seconds. Again, take it to 4 significant figures because you need to make sure your final answer is correct to 3 significant figures. Then over here, time is 1.73 seconds. Now we can find the total time if you include the original 0.5 seconds that it takes for them to collide. That's kind of up to you whether or not you want to include that. So that's what the 0.5 is, the original collision time. Then the time that it takes the coalesced object to reach its final highest point by going up, and then the time it takes for the coalesced object to get back to the ground. You add all of those up and you get 4.236 seconds or 2.732 seconds. If you chose not to include that, because you can basically take it away from both of them and still be okay with it. It's taking the same amount from both times. And this is what the mark scheme does. The mark scheme doesn't include the 0.5. I did. So if you take without that initial 0.5, then you get 3.736 seconds and 2.232 seconds. Now it's asking for the difference between the two times as when the objects hit the ground. These times here are after coalescence. This, including the 0.5, was before coalescence. Either way, whichever one you do, your difference will still be 1.50 seconds. Make sure you put the 0 because it's to 3 significant figures. 1.50 seconds is the total. So it's a lot of work. You've got momentum in here. You've got suva in here. You've got projection. You have being dropped from rest. You have the objects colliding and coalescing, the momentum driving the object back up until the velocity, till gravity basically makes it stop, and then it falls back to the ground. You got 2 scenarios because the mass can be 1m, the other one 2m, and vice versa. And then solving for T in each of those stages and adding them all up. So this was quite a big question. 8 points. You should be able to do that in about 10 minutes. And I know that looks pretty rough to do in 10 minutes. So you're gonna have to kind of work through it quickly to get this done in 10 minutes to get that. You might have a little more than 10 minutes, basically 10 minutes is about what you have to get that question done. So that one's pretty rough, pretty complicated. Now let's go down to our last question here, number 7. Particle P moving in a straight line starts from rest. There's the 0 at point O, comes to rest again 16 seconds later. So, oh, sorry, this 0 is time 0, but so velocity is 0 at 0 seconds and velocity is also 0 at 16 seconds. At time t seconds, the acceleration is given by these 3 equations. So the first one is acceleration is a function of time. That means for this interval, you're using calculus. Don't forget that. Acceleration is a function of time. For the second interval from 2 seconds to 4 seconds, acceleration is constant. That means you're using Suvat formulas. For the third one, it's again a function of time. So from 4 to 16, you are again using calculus. There is no sudden change in velocity at any instant, which means your velocity from the end of one interval should be the same as the velocity at the beginning of the next interval. Find the values of t when the velocity of p is 55. Notice it says values plural, so there's going to be 2 when the velocity is 55. So we need to find out which interval we're dealing with that gives us a velocity over 55 meters per second. So let's start with our first one here. And we're going to use calculus. So we integrate our acceleration function to get velocity function, because we need to find the velocity for 55. And so when we integrate it, remember, add 1 to the exponent and divide by that number. So you get 6t plus 2t squared. If you want to just take the derivative real quick to make sure that you did it right. So when you plug in a time of 0, of course, you have a velocity of 0. When you plug in a time of 2, you end up with a velocity of 20 meters per second. Then we go to our second one. Our second one is constant. Okay. So because it's a constant acceleration, that means your velocity is going to be linear. Okay. So when we look at this, our final velocity is going to be our initial velocity. Our initial velocity is not the 20. The 20 is the initial velocity only for this interval. It's not the initial velocity for the formula. Okay, so be careful with that. The initial velocity is not the 20. The 20 is for at t equals 2. What we want is our initial velocity for when t equals 0, and that's not this 0 up here. Well, it is this 0, but it's not with this formula. Okay, so our final velocity is our initial velocity plus 14t, because we have 14 here. In other words, you're kind of integrating this as well, 14t, and we want this to equal 20 when t equals 2, because this is a coordinate that we know that the final velocity is 20 when t is 2 seconds. That is the final velocity from 0 to 2. So plug in 2 for 2 seconds, 20 for the velocity at that point, and you're going to find out that the initial velocity, that is for this equation, is -8 meters per second if you went all the way back to t equals 0. So that gives you a finished product here of v of t equals 14 minus 8. Now we can predict outcomes. So when we plug in our 2 seconds, we do get a velocity of 20. That agrees with our previous measurement. And when we plug in 4, we now get 48 meters per second. Then we go to the third one. we use calculus again. Integrate that 16t minus t squared. And when you plug in 4, you get 48, which is also an agreement here. And when you plug in 16, you do get 0, which makes sense if you factor this and set it equal to 0. You see that the two places where velocity is 0 is when it starts at rest and at 16 seconds later. Now, which one of these has the velocity of 55? Well, this one is going from 0 to 20. This one is from, and this is an upward facing parabola. Okay, so we're going from lower to higher. This one is linear, again, going from 20 to 48. This one is a downward facing parabola. So the 48 is not the maximum. It keeps going up and then it will go down until it hits 0. So the 55 is going to be in this section here because it's a downward facing parabola. So change this into a quadratic, factor it, solve for 0. The 2 points at which it's going 55 meters per second is at 5 seconds and at 11 seconds. The second part of this wants you to complete a velocity time graph. Well, we already figured out all the velocities from 0 to 20, 20 to 48, and then 48 back to 16. We need to calculate the maximum velocity. So notice from 0 to 2 is an upward facing parabola. And that was also from 0 to 20 meters per second. So make sure it's parabolic, not linear. Then the second equation they already put in for you. It is linear from 20 to 48. That one is linear. And then the third equation is a downward facing parabola. So you need to figure out where that maximum point is. And you know that this goes actually from 0 to 16, but the part that we draw is only from 4 to 16 because of right here, 4 to 16. But we also know from this that it does start at the origin 0 and 16. We can see that here as well. So even though this continues down to 0, we don't need to draw that part. We only draw this part. So halfway between 0 and 16 is 8. You can plug your 8 in. I don't know where I did it, but you plug 8 in, and maybe I just did it in the calculator, and you get 64 meters per second is your maximum when you plug 8 into this right here. So this says find the distance traveled when particle P, by particle P, when it is decelerating. Well, if you look at this part here, this has positive slope. It's accelerating. This is also positive slope. That's accelerating. And this third one has part of it is still positive slope. It's still accelerating until it reaches the 64 meters per second, at which it stops accelerating and then starts to decelerate. Now we have negative slope. So it's starting to slow down until it reaches 0 meters per second. So we want the interval from 8 to 16. And we are using that third section formula, the 16t minus t squared. It wants us to find distance. So we need to integrate again, get at squared minus 1/3 t cubed over the interval of 8 to 16. I didn't show the integral sign with its bounds of integration. Instead, I've just integrated it and showed it over here for the evaluation. So you plug in the 16, you get 682.67. Plug in the 8, you get 341.33. You subtract those because it's top minus bottom, and you get 341 meters to 3 significant figures for that. And there we go. That's the end of this mechanics past paper. I hope it's helpful for you. Thank you for joining me in the Zoom room, and hope to see you again next time.